Hello, I'm going to do section 1.4, number 8 to start off with. So here we go, 1.4, number 8. Okay, what are we trying to do here? It says, find general solutions, implicit if necessary, explicit if convenient, of the differential equation in problems 1 through 18. Primes denote derivatives with respect to x. Okay, so here's the differential equation. Dy dx is equal to 2x secant of x. Okay, so we're going to first put this in our nice form by gathering up, it didn't look right actually. This is a y, secant of y. All right. Secant y. Okay, so first we need to rewrite this. So we can rewrite this as dy divided by the secant y is equal to 2x dx. Okay. Now what we can do is integrate both sides. So if we integrate this side with respect to y, we will get must have this equal to the integral of this with respect to x. Okay, so now the secant of y, we can write that as that's 1 over the cosine. Okay, so really we can write this left-hand side as the integral of the cosine of y with respect to y has to be the integral of 2x dx. Okay, now we can easily integrate these things. The cosine of y, integral of the antiderivative of the cosine of y is the sine of y plus some constant. I'll put it in C1. That would have to be equal to, well, this is just x squared plus some other constant, C2. Okay, let's now solve this for y. First we'll write down that the sine of y has to be equal to x squared plus just some other constant, c. Actually, it would be c2 minus c1, but it's just a constant. Then if we take the inverse sine of both sides, we see that y is equal to the inverse sine of x squared plus a constant. And there we have it. Okay, the next one I'd like to do is just number 21. Let me read the instructions here, or what they want us to do. It says, find explicit practical solutions of the initial value problems in problem 19 through 28. So I'm looking at number 21. Let me write down what the differential equation is that we're trying to solve. Okay, so we're trying to solve the differential equation. Here we go. 2y times dy dx is equal to x over the square root, depending on how you say it, of x squared minus 16. And let's see, the initial conditions are, we know that y at what is it? Oh, at 5, when x equals 5. I'll make that look a little bit better here, sorry. So when x is equal to 5, okay, we know that y is equal to 2. Okay, let's solve this here. So what we'll do is we'll integrate. Well, first off, let's rewrite this. We have, so 2y dy has to be equal to x, the square root of x squared minus 16 dx. Okay, so then we're going to integrate both sides. And let's see, the left-hand side is easily calculated. Let's work on the right-hand side. So looking at the right-hand side, I'm going to make the substitution u is equal to x squared minus 16. So then du is the derivative of x squared minus 16 with respect to x, or 2x, and then dx. So what we see is that I can rewrite my integral. Okay, so the integral of x all over the square root of x squared minus 16 is the same as, well, I have to make my appropriate things here. Well, x dx is actually equal to du over 2. So there's there we go there. Right? And then I have the square root of u. Okay. And then anti-differentiating this, we see that this is equal to what? Okay, so this is actually just u to the 1/2 plus a constant. All right. So that means that substituting back in for u, we see that the integral of x over the square root of x squared minus 16 dx is equal to x squared minus 16 to the 1/2 power plus a constant, which leads us to our general solution here of the differential equation, which I'll write down. If I integrate 2y, I would get y squared. Then combining the constants all on the right-hand side of the equation, this y squared would have to be equal to x squared minus 16 to the 1/2 power plus a constant. Now let me look back to see what our initial conditions are. You see, our initial conditions were that y, when x is equal to 5, y is equal to 2. All right, so let's see what that means. So when y is equal to, well, when x is equal to 5, y is equal to 2, so I must have that 2 squared is equal to this 5 squared minus 16 to the 1/2 power plus this constant. Oops. All right. That's a plus sign right there, by the way. So here, let me clean that up a little bit. Okay. Now, okay, so what does that mean? So we have 4 is equal to, let's see, this mess is 25 minus 16, which is 9, and the square root of that is 3, plus a constant. So we see that the constant must be equal to, that's an equal sign. Sorry, my little pad here is not acting very well. So this is equal to 1. So our solution to the initial value problem is that we have to have that y squared is equal to this, gosh darn it. My pad is not making me happy right now. All right, so that has to be equal to what? Okay, so basically substituting in there, we get y squared is right this way, the square root of x squared minus 16 plus 1. And that's our solution. Okay, next one I want to do is this number 37. I'll read this. It's a nice application. It says, continuing compound interest. It says, upon the birth of their first child, a couple deposits $5,000 into an account that pays 8% interest compounded continuously. The interest payments are allowed to accumulate. Okay. How much will the account contain on the child's 18th birthday? Okay, so let me write down the information that we have. Let's use y to represent the amount. So we have y at time 0, when this whole thing starts, is 5,000. Now, here's the in your text, and there's this differential equation that, you know, dy dt, when something is growing with respect to this model. This is the model that is used to define continuous interest, compounding continuously. So if you solve this equation, actually let's solve this once for practice using our technique here. So we want to solve this equation here, where r is the rate. So r here in this case is 0.18. So in other words, the instantaneous rate of change of y with respect to t is equal to 0.18 times y. Okay. Here t is in years, because the interest rate r is in years also. Okay, so let's solve this here. So to solve this, we would then rewrite this as dy over y is equal to r dt. Now, integrating both sides, which I'll just save some writing by doing this. So the integral of this is the integral of this with respect to the respective variables. So this we have is the natural logarithm of y. And over here, this is just rt, and it's plus a constant. Now to solve such equations, we invoke the exponential function. Okay? So we know that if I take and exponentiate both sides, here I have y is equal to e to the rt plus c, which can be rewritten as, here I'll just do it, it's e to the rt times e to the c. So normally how you see this is the following way. Y is equal to some constant k, that's our e to the c, times e to the rt. And that's how one can derive the solution to such a thing. Now, we're given the information that y at time 0 is 5,000. So we can clearly see that the equation for the amount of money in this account at time t is given. Oops, I think I wrote the wrong thing down here. Hold on. I wrote down 18%. Actually, the interest rate, I must redo this. The interest rate was actually 8%. Okay, so the r is 0.08. And okay, so that means that I have to get rid of this. Okay, so the interest rate is 0.08 times t. Okay, now the question is, what is the value of this account after 18 years? So there we just simply calculate the value at time t is equal to 18. And if you drag out your calculator or a computer or whatever you happen to have sitting around you, you can see that this is approximately equal to What did I come up with here? $21,103. Excellent. Okay, so that's number 37. I'd like to do one more. This would be number 40. Okay. Let me get a new sheet here. All right, here we go. So number 40 in the same sort of section. I'll read this one to us. Okay, it says the half-life of radioactive cobalt, all right, is 5.27 years. Suppose that the nuclear accident has left the level of cobalt radiation in a certain region at 100 times the level acceptable for human habitation. How long will it be until the region is again habitable? This is ignore the probable presence of other radioactive isotopes. Okay, so let me translate all these words into mathematics. So we know from our from what we've read in the book and our previous calculation that if we're using this stuff grows and decays exponentially. So the solution to this is of this form: y of t will be equal to some constant k times e to the rt. In this case, our r will be negative since things are decaying. Now let me translate the pertinent information. Let's assume for our calculations, let's say that the acceptable level is 1. Okay, so that would mean that one quantity of it. So I'd say y at time 0, then I could just set that equal to 100. So then the question is, if that's 100 times 1, right? What we're trying to do is we're trying to find some time t, and I'll call it t final for some reason, so that y at t final it basically is less than 1. In other words, we're finding some period of time when we can basically move back in. Okay? All right. Now, half-life means the definition of that word in mathematics is that's the amount of time it takes for the amount of radiation to decrease to half its current level. So that means that we have that y at 5.27 years is equal to 50. Okay. All right. Let's go ahead and see what we get here. Okay. So let's try to find out what we can. Well, we know k is equal to 100. Okay. So the two bits of information we know. Well, we know this. We know y at t is definitely equal to 100 times e to the rt. Okay, and in fact, if I plug in here, I also know that 50 is what we get when we plug in. What was it? 5.27. So that's equal to 100 times e to the rt. So what we're going times 5.27. We will now use this equation right here to try to solve for r. So if we're solving for r, what we really want to do is solve for e to something first. So we see that 1/2, it has to actually be equal to e to the r times 5.27. Now, just as when we solve logarithmic equations, we exponentiate. If we're trying to solve exponential equations, we take logarithms of both sides of this equation. So this implies that the natural logarithm of 1/2 is equal to r times 5.27. Solving for r, we see that r is equal to the natural logarithm of 1/2 divided by 5.27. And now if you grab your calculator and start banging away on it, you'll find that r is approximately equal to, oh, that's a weird looking thing. Let me fix that. So we see, I'll write from left to right. Okay. So then if you do your calculations here, what you will find is that r is approximately equal to, I came up with negative 0.131. Okay? All right, so this, well, that's all right. So that says that we finally have our equation. In other words, that, we know what our equation is for y times t. And what we're trying to do now is let's find out how much time it takes to get down to level 1. In other words, I'm going to solve the following equation. I'm going to solve, I can just get in here, I'm going to solve, sorry for the 1 equals 100 times e to the negative 0.13 times t. So to solve this equation, we again would use the logarithm function, and in fact, what we're going to do, we'll first solve for the exponential. Okay. Taking logarithms, we see that the natural logarithm of 100 is equal to negative 0.13. Ah, son of a gun again. I gotta this darn thing. I hate to have to get my pad redone here or something. It's 0.13 t. And then solving for t, what you find is that t is approximately equal to, let's say, 35.4. And that's in terms of years. Now, okay, so we did this calculation, and let's just see if it makes some sense. So I just, it's always good to make sure your answers make sense. So if you look at this chart here, here's what I did. If you look here, see that's the 100 that it started off with at time t equals 0. So this is actually y, and this is t. So notice at time t equals 0, we get 100, 5.2, 50. And so what you'll see is these numbers are, I'm dividing by 2 in each of these blocks. And here I'm increasing by a 5.27. And if you look here closely, you'll see that in year 36, we're approximately at 5.8. So the answer r equals 35 is plausible. Okay, if you have any questions, again, please call me at area code 414-828-4111. I hope you enjoyed this. So thank you. Bye-bye.